Hi, everybody. I'm here to introduce Predrag. He is known for developing cargo-semver-checks as a semantic version in linter for Rust. And also, he worked on diverse range of data systems, including relational and graph databases. One of the project of him with the data is Trustfall, the universal query engine capable of querying any data source. And this is actually the topic of his talk. Predrag, you can unmute yourself and show up. Thank you. And now I have to say two technical questions. First, if you want to ask a question, use the QA button in the bottom of your screen. And also you can turn on captions in any language. Zoom will translate the speech for you. And now the stage is yours.
Thank you. And thanks to everyone organizing this conference for making it happen. It's my pleasure to be here. As Paul mentioned, my name is Predrag, and I work on a wide variety of tools. Trustfall and cargo-semver-checks are just some of what I work on. And it's my pleasure today to talk about how Trustfall represents a foundation for next-generation developer tools. As Paul mentioned, I'm probably best known for my work on cargo-semver-checks and Trustfall. So we'll be talking about both of those today. Even though Trustfall is the nominal topic of this presentation, cargo-semver-checks wouldn't be possible without it. And because cargo-semver-checks is probably the more popular of the two tools that I work on, a lot of my examples are going to involve how cargo-semver-checks benefits from Trustfall's existence. And in case you might not be familiar with my tools, you might have read some of my blog posts. I write on a lot of topics, including a variety of Rust functionality and how I've discovered it to work as part of working on cargo-semver-checks. I read a lot about Semver and finding unexpected breaking changes in many places. And every so often, I have some fun and write about topics like the time that I had to debug a Wi-Fi connection that only worked while it was raining outside. So if these sound interesting, you can check out my blog and I'll make sure you have a link to it later in the slides. But now back to our topic. Let's talk about Trustfall and how it makes next generation developer tools possible. First, I think it's useful to define what is a next generation developer tool. I'd like to define it as a tool that helps us catch as many problems as possible, as early as possible, as quickly as possible. So that means we want to catch these problems at compile time, not at runtime. We want to catch them in the pull request that it causes the problem, not in production in real life. And we also want to catch these problems as quickly as possible in milliseconds, not minutes. So even if we have a large project, it's still not acceptable for a tool to be running for minutes and hours. That's just not a very good developer experience. We want that to happen as quickly as possible. And I'd like to posit the cargo-semver-checks is exactly that kind of tool. It's designed to run right in your publishing workflow. You're supposed to run it as cargo-semver-checks right before you run cargo publish, and therefore it has to be very good at what it does and quite fast. The idea here is that cargo-semver-checks will detect the version bump that you're about to publish, and then it will scan your package for API changes that are inappropriate for that bump. So if you've made an accidental major breaking change, and you're not releasing a new major version, that's a problem that you should probably take a look at before you release it into production, into the real world. And I'm pleased to let you know that cargo-semver-checks is actually planned to become a built-in part of the publish command itself. So in the future, you won't have to run two commands here. Cargo publish will run cargo-semver-checks for you under the hood. And that's super exciting, and I'm thrilled to have the cargo team's support on this. It's also a very useful tool already. We've run cargo-semver-checks over the top 1,000 most popular crates in the entire Rust ecosystem, and we found that more than 1 in 6 of them have accidentally broken semantic versioning at least once. We found that result quite surprising, and to really understand what this means, I want to tell you a little bit more about what we mean here exactly when we say broken semantic versioning. It means that they published a major breaking change without making a major version bump in their package. So this means that a user that ran cargo update would pull in the new version, But because there's a major breaking change, it's possible that their project no longer works. It might have compile errors, it might trigger undefined behavior, it might have some kind of undesirable effect on their project that was not appropriately communicated through semantic versioning. As we all know, versions normally have three components separated by dots, so major, dot minor, dot patch. But what most people might not know is that the implementation of semantic versioning in Cargo is a little bit particular. It ignores leading zeros. So more things count as major bumps in Rust than one might assume. So 1.0 to 2.0 is a major bump, but so is 0.1 to 0.2, because we ignore the leading zeros and the leftmost non-zero number got bumped. So it's totally fine to publish major breaking changes if you're going from 0.1 to 0.2. And we found that more than 1 in 6 of the top 1,000 crates went, say, 1.1 to 1.2 while making major breaking changes. That's the problem that we're looking for with cargo-semver-checks. And the interesting thing here is that this happened to a lot of experts. These top 1,000 most popular Rust crates are the ones that are maintained by the people that know Rust and the semantic versioning rules and the implications of accidentally breaking Semver better than anyone else. If they're having trouble upholding semantic versioning in their packages, what hope is there for the rest of us? So cargo-semver-checks is a valuable tool because it helps all of us do better. This is not a tool that we grow out of because we learn all the rules and then all of a sudden we don't need it anymore. No, all of us need this, and all of us are better off if everyone uses cargo-semver-checks in their publishing flow. So now you might be thinking, next generation dev tools, they sound great. How do they work? At a high level, cargo-semver-checks does two things. First, it identifies what is the previous release that your current release, the one that you're about to make with Cargo Publish, relates to. And then it will run about 80 checks between the APIs of the two releases. It will look for example, public functions that disappeared. So someone that was using that function, their code might be broken now. Or a public type that stopped implementing some trait. If some downstream user was depending on that trait being implemented to that type, then that code doesn't work anymore, and so on and so on. So we have about 80 of these checks that we run in cargo-semver-checks before you release the new version. To give you a sense of what that looks like, here's a screenshot from the cargo-semver-checks repository from its lints directory. And every file that you see in this list represents one check. It defines all of the rules that are necessary to check semantic versioning for that specific rule. And this is more of those files, and some more of those files still. And believe it or not, this is still not a complete list. There are still rules that did not make it onto here. So I want to peek under the hood and show you the scope of the challenge that we're facing here and how all of this works, so that you can get a full appreciation of what the Trustfall query engine gets for us here. And like I mentioned, Trustfall is a query engine for any combination of data sources. It lets us query files and APIs as if they were databases. And right now you're probably thinking, what does database querying have to do with dev tools? That sounds weird. So let's dive right in. Let's talk about what we have to do here. And the thing I'm going to try to convince you of is that next generation dev tools are actually a database problem in disguise. And again, we'll talk about this through the lens of cargo-semver-checks. So I'll walk you through what does it mean for a specific lint, for a specific check for a major breaking change to be implemented in cargo-semver-checks in all of its glory, with all of the edge cases that we have to worry about and all of the challenges that we have to overcome. So the rest of this talk is split into three sections. First, we're going to look at the details of the Semver breakage that we want to catch, including all of the edge cases we have to worry about. Then we'll take a look at the technical challenges that we had to overcome. So not the intricacies of semantic versioning, but just what would it take for a tool to exist that catches this problem. And having seen both the edge cases in Semver and the technical challenges, we'll see how Trustfall helps us do better. Let's dive right in. Let's talk about Semver breakage. The easiest possible aspect of Semver breakage is this: a public function used to exist and it got deleted. So on the screen here, I'm showing the GitHub pull request view for a public function being deleted. Now, you might think this is super clear cut. obviously a breaking change, right? Anyone that used this function is now broken because it doesn't exist anymore, so they can't import it, they can't call it, their code is broken. And you're right. If you run cargo-semver-checks, it will tell you the same thing. It will say the function missing lint failed. It says a public function was removed or renamed. It identifies the function called add that was previously defined in this lib.rs file on line number 1. And it says Semver requires a new major version. You weren't publishing a new major version, so this is a problem. Please take a look. And this is pretty simple, right? Deletions of public items are always a breaking change, so we didn't really need the tool here, right? We could have caught this by eye. This is just totally fine, right? Well, as it happens, this is a lot more complicated than it might look at first glance. And the first example of that I want to show you is the following. So here we have that same kind of thing. We have a public function called example, but it's defined inside a private module. And because it's defined inside a private module, it can't be imported from outside this crate. So deleting it is not a breaking change because nobody could have imported this function. And because they couldn't have imported it, they couldn't have used it. So if we delete it from here, nobody could be broken because nobody's using it. That's one case where we might be able to delete a public function completely safely without causing any sort of breakage whatsoever. Another interesting example is a little bit more tricky. We have a similar setup. We have a public function, and it's defined inside a module, but the module is now public. And not only is it public, it's also marked with this doc hidden attribute. Now, doc hidden is an attribute that we use to document components that are defined as public, but they're explicitly not part of the public API of the crate, of the library. This is useful because a lot of the time, packages define macros. And when those macros expand, they can only rely on public code from the crate that defined the macro. Now, macros do a lot of magic, and the magic that they rely on isn't necessarily intended to be used directly. It's intended to only be targeted by the macro and by nothing else. But we can't make that magic private, because if it's private, then the macro expanded code won't be able to access it. It will just be a compilation error. So we need this sort of third state of being, where code is public, but it's not public API. So nobody is expected to use it directly. Only macros are allowed to use it. And in order to express that, we have this doc hidden attribute. When we mark the module doc hidden, it means this module and everything inside it is not public API, so you shouldn't be using it. You shouldn't be depending on it directly. And when macros depend on it, it is the macro's responsibility to be updated appropriately to account for any breaking changes. This means that deleting this example function by itself is not a Semver major change. If whatever was depending on it gets altered appropriately like a macro, everything's good. This can't cause any breakage. And so you might be thinking, okay, if the function is defined inside this doc hidden module, then again, we ignore it. Pretty clear cut, not a problem. Well, as it turns out, the rule is even more complicated than that. Here we have the opposite example. We have a public function that is still defined inside a public module that is doc hidden, but now the function itself is re-exported at top level without being doc hidden. And now the function is public API, even though it's defined inside a doc hidden module. Users can import it directly by saying use this crate : example. And that invocation never touches any non-public API. Nothing in that use statement is marked doc hidden. So this is fair game. This example function at top level in this crate is public API, and deleting it is a major breaking change. Now, we took the simplest possible rule about deleting public functions, and we found that it's full of edge cases already. This is why cargo-semver-checks is super valuable. This is why even experts can often get this stuff wrong. And because the simplest rule is already so complicated, what about the rest of the rules? We said we have more than 80 of them, and there are hundreds more rules that we are still working on implementing. So you can see that there's a lot of complexity that we have to get exactly right here. That is part of the difficulty here of having a tool like cargo-semver-checks. And in the rest of this talk, I'm going to tell you more about how all of that works. In cargo-semver-checks, like I mentioned, we have 80 lints, and more get added every week, even though they're correctly handling an astonishing number of edge cases. And cargo-semver-checks is a tool that is widely used and loved. Key Rust projects like Tokyo and Cargo use it, and also companies like Amazon, Microsoft, Google, Cloudflare, and so on. And their users love it because it's always better to catch these accidental breaking changes before they go into production, and annoyed users open a GitHub issue saying, hey, you broke my project, please don't do this. So now that we understand the semver breakage that we're trying to catch, let's take a look at some of the technical challenges that we have to overcome in order to ship this in the real world. I already hinted this a little bit. We not only have to catch the problems, we also have to do it early in the process and very quickly. And this already gives us a clue. We have many problems to catch. Like I said, we have 80 already implemented, but we have hundreds more to go. So there's a very large problem space that we have to cover. We have to do so with very good performance. We're running dozens of lints, and we want this to run in milliseconds. This is a big enough topic that I actually gave a conference talk on this specifically at a conference called P99 last year. And I put a link up to that talk over here, and I'll make sure that the slides are available to you after the talk, so you can check out this talk if this is something that's interesting to you. But not only do we have to have really good performance, we also have to deal with the fact that our input data format is unstable. More or less every new Rust version comes with a new Rust.json format, which is the data that we use that is derived from the Rust compiler that tells us what is and is not public API. This format has a bit of complexity in itself, and Luca Palmieri actually gave a great talk at this conference last year about how it works. I highly recommend you checking it out in case this is something that you're interested in learning more about. This Rust.json format is excellent because it comes directly off of the Rust compiler, but as the Rust compiler and the language itself are changing, we have to accommodate the fact that this input data format is changing as well. And the biggest challenge of all is that we have to do all of this maintainably. We have a very, very large surface area to deal with. We have to write and maintain countless lints. We have to support Linux and Windows and Mac OS on x86 and ARM. We have to support multiple Rust and Rust.doc format versions. And we have to maintain correctness and good performance with only one maintainer and minimal funding as an open source project. It's not like we have a department's worth of people and millions of dollars to do this with. No, we have a set of contributors and one maintainer and very little funding like most open source projects. And yet we have to deliver a tool that everyone loves and that makes everyone in the community better off when everyone is using it. So in short, we have complexity everywhere we look. There's no escaping it. And the only way that we can get this done is if we abandon traditional approaches and try something different. So I want to give you a bit of a sense of how these traditional approaches work and why they wouldn't work here. If we wrote the rules for checking semantic versioning in the traditional imperative sense, kind of how like Clippy does it and kind of how almost every linter under the sun works today, it would look something like this. Our lint that looks for missing public functions would look something like this. We would have a for loop over all the public functions in the old version, and we would have a matching for loop over all the functions in the new version. We would try to match them up by import path. And if we find a function that is at the matching import path, we say, okay, this function exists. The user is able to import it, and so this is not a breaking change. It's all good. And if we didn't find the function at the same import path, then clearly there's a function that's missing, and so we will raise a lint and we will complain about that function being gone. This seems fine. There's just a couple of problems here that you might have already noticed. The first obvious problem is that this is actually O of n squared. Oops. If we have a lot of code, this will be very slow. This is not an unsurmountable problem. This is something that we could fix. But it will get quite annoying when we have to optimize every single lint separately for every aspect of performance. This is something that would be extremely burden-inducing on the maintainers and on the contributors, and so we'd rather not do it if we could avoid it. Another problem is that this approach would be very tightly coupled to the underlying data format. Our linter would be sitting directly on top of Rust.json without any intermediate representation in between. And so that means that all of the rules reference the specifics of the format directly, and in practice, that means the end users must know which version of the linter corresponds to which version of the Rust.doc format, and by extension, which Rust version. So they would have to know, oh, with this Rust version, you use that version of the linter, and with that Rust version, you use this other version of the linter. This is possible, and some tools do this, but this is not the best user experience. It's not great. So we'd like to avoid it if we can. But the worst problem here is that this leads to poor maintainability. If we're going to have on the order of a couple hundred lints, and we have a new format every few weeks, and we're tightly coupled to this format, that means that we need to rewrite these lints to adapt for the new format every 6 weeks or so. And we have to make sure that we get all the optimizations right, and we have to make sure that all the correctness is still good, that we still catch all of the edge cases. And that sounds like a recipe for burnout to me. It doesn't really leave a lot of room for building new features or for performance improvements or for really any other work. This sounds like it will be more than a full-time job by itself. So traditional approaches are going to struggle in this domain, and we have to try something different. Here is where the database problem in disguise part comes in. If we take a look at the problem for 10,000 meters up in the air, we're going to notice some interesting things. Our lint boils down to more or less find public API functions that used to exist but don't anymore. And if we put our database hat on, we might think, okay, this sounds like a database query. Select star from items where type equals function and visibility equals pub and so on and so on. Maybe some joins and things like that in there. And yes, the underlying Rust doc format might change, but in database land, again, database hat on, we just call that a view, right? We create a view that abstracts our queries from the underlying data format representation. So yes, the underlying tables change, but our view doesn't change, and so our queries are not broken. And we need to optimize these similar operations across all lints, right? We want to make finding missing functions faster and also missing structs and also missing enums. And in database land, with the database hat on, this just sounds like a create index operation. So it really sounds like there's a database problem that we need to unearth here and dig up and plug in somehow. And in fact, that's exactly how cargo-semver-checks is built. Instead of attaching the linter directly to the Rust doc format, we attach the linter to Trustfall, and we attach the Rust doc format to Trustfall as well from the other side. So we have this architecture diagram that shows us how Trustfall is sitting in between cargo-semver-checks and the data format under the hood. We write our lints as declarative queries in this world that are loosely coupled to the data format, and I'm going to show you what this looks like in practice. But the end result is that we can support multiple Rust versions and Rust doc formats with the same exact cargo-semver-checks version. So users don't have to worry about, will this version work with that Rust version? We can just support multiple of them, and one binary does everything. Because our lints are declarative, it means that optimization is easy. Optimizations are applied automatically. They're not mentioned in the lint itself, and this makes it very easy to apply optimizations because most of the time you're not even aware of them at all. And this is very contributor friendly. Because the lints are easy to write, they're even easier to review. So in fact, most of the lints in cargo-semver-checks are other people's contributions. I don't tend to write lints. I tend to focus my attention as a maintainer on making cargo-semver-checks a more successful tool in other ways. And lots of other people end up contributing lints to the tool all the time. Every new version of cargo-semver-checks comes with brand new lints that weren't there before. So if that's something you're interested in, please check it out, and I'm sure you could write a lint by learning everything that you're going to learn off of this talk and nothing else. So now that we understand the challenges that we had to overcome, let's talk about how Trustfall makes all of this easier. Like I said, we're going to be facing multiple different data formats under the hood, but at a high level, the data is still the same. The schema hasn't really changed. Rust APIs are built up from the same components every time: functions, structs, fields, enums, variants, and so on. So in principle, we should be able to define a schema that doesn't depend on the JSON format itself, and then use that schema to express all of the lints that we're interested in. We're going to model our data as a graph. What we're going to do is describe Rust APIs as a set of vertices that have properties and that have edges connecting them. So on the right here, you can see the vertex type definition for a Rust function. You can see that it has some properties called name and deprecated and visibility limit. These are things that come from item, which is a super type of function. So we have this type hierarchy for vertices as well. Functions, structs, enums, they're all items in Rust parlance. And they all share the fact that they can have docs, they can be deprecated, they could be public or private, and so on. But functions also have some of their own properties. They could be const, they could be unsafe, they could be async, and so on. And then there are also some edges connecting functions to other types of vertices. Functions might have attributes, they might be importable by some paths, they might have some parameters, and so on. And if you're comfortable with the SQL or relational model, you'll notice that this is very, very similar, but it's maybe a little bit more convenient in some ways. If you're familiar with SQL, you'll notice that a vertex is kind of like a table. The properties are kind of like columns on that table, and the edges are kind of like foreign key relationships between different tables. But when I say it's more convenient, it means that we can model this to be more closely matching what our intuition represents for Rust. So in SQL, it's not that you can't model the fact that a function is an item. You can. It's a little bit annoying sometimes. And it's not that you can't add custom edges like importable path. They're not in the underlying data source. It's just a little bit more complicated. In Trustfall, we just say importable path is a particular type of edge, and it will get transparently computed on demand via some code that we get embedded into Trustfall. We don't have to worry about it when we're writing lints. What this means is that when we see this architecture diagram, from the midpoint up, everything that happens is just this data graph that is described by our schema and that has these declarative lints written over it. So cargo-semver-checks has no idea about the underlying JSON representation that changes in the format anything. And everything in the bottom half has no idea about cargo-semver-checks, semantic versioning, anything like that. All it knows is how to take the Rust stock JSON formats and adapt it to satisfy this schema. So it doesn't know anything about the queries. It doesn't know anything about the semantic versioning business logic. All it cares about is being able to fulfill requests over that schema. That's it. This is a very, very strong abstraction, and I'm going to show you how we make use of this. Let's talk about how we query this graph. So we're going to look at this. We're going to look at some queries, and I'm going to show you a diagrammatic representation of the shape of the graph that we're going to look for in our queries. So anything that you see that is this hand-drawn style represents a query graph, something that we're going to attempt to match in the underlying data representation. So let's try querying for all the functions in a given crate that have, and all of their importable paths and whether they're public API. So this is 3 vertices, the crate, the function, and the importable path. And we're going to pull out some properties like the name, the path, and public API. So on the left, you see this query in Trustfall query syntax. In the middle, we see that diagram representation. And let's run this by a few different crates and take a look at what running this query in Trustfall would give us for each of them. Let's start with the simplest example where we have this public function at the top level of our crate. When we run this query, we get that the name of the function is example, the path is this crate : example, and it's public API. So public API is true. That's just a Boolean property. This is pretty straightforward. We probably didn't need Trustfall for that. So let's dig into some more complicated cases. Let's take a look at some of the cases we talked about earlier that were edge cases in our function got deleted from the public API case. So here we have a private module and a public function inside it. If we run this query, there are no importable paths here. That importable path edge from function does not exist. For this function, no such edges. Because that edge is required when we run this query, we get no results. This is already pretty good. If we ran this query and asked for what is public API, we don't get this function. So you can already kind of see how we're going to use this as a building block in assembling the bigger lint. Let's take a look at another example that we talked about earlier. Here we have that case where we have a public function inside a public module that is doc hidden. So again, we run this query. There is an importable path. It's this crate : macro helpers : example. But we now see that it's not public API. The public API column says false. And it's not public API because the Trustfall query engine and its underlying adapter has determined that this function crosses through something that is doc hidden when accessed through this path. And as a result, the public API property is false. So this is already very nice. We didn't have to worry about attributes and how all of this code is aligned. We just get a false property and we know that this is not part of our public API. And finally, let's try that trickiest case of all, where we have the doc hidden module, but the function is publicly re-exported at the top level. When we run this query, we actually get two results, not one, because there are two different publicly importable paths. One is through the module and one is top level. Now, through the module, this function is not public API. So if you accessed it through macro helpers, you go through a doc hidden boundary and public API is false. But the direct importable path that does not cross through doc hidden is public API. And if we take a look at that field in the table, we see that that right there is true. So this will let us write the lint for which public functions got deleted very, very easily, because we didn't have to worry about the logic of re-exports and how doc hidden works. We just wrote a query, Trustfall ran it with all available optimizations, and we got a table of results back. So if we go back to our example where a public function got completely deleted, we can now see how we can assemble a full query. This is the diagram representation of the entire lint that is in cargo-semver-checks today. We're looking at a version pair that has the old version and the new version. The old version, we're going to be looking at functions, and we're going to be looking at importable paths of those functions. In the new crate, we're also going to be looking at functions, and we're going to try to find one that matches the same importable path as the one that we were looking at in the old crate. If we find it, great. That is not a breaking change. However, if we don't find it, that means that we have found a breaking change. And if we didn't find it, we're going to express that by saying, if we count up how many functions at the same importable path exist in the new crate, that count is equal to 0. So let's take a look at what that looks like in the Trustfall query engine. Our lint, the full lint logic is this. We want to say previously the function was public, another crate could have imported and used it, the import did not rely on any doc hidden items, and the same import name no longer satisfies the above. So that count is 0. And in Trustfall query syntax, this is what it looks like. This seems like a lot of code. It might be a little bit intimidating, but if we walk through it step by step, we'll see that it exactly matches the description on the left-hand side. Bear with me here. We start by looking at items in the old version. We only look at functions, so we discard everything that isn't a function. We make sure that the function is public, so visibility limit equals public. We make sure that there is an importable path that another crate could have imported and used that function. And that import is public API, so it did not rely on any doc hidden items. And if we look at the same exact importable path in the current version, in the new version that we're about to publish, that same import, when we count up how many functions at that importable path match our query, we see that fold, transform, count equals 0, right? So we find 0 of those matching functions. That's it. This is the real function missing lint from cargo-semver-checks. This is the real lint file in the cargo-semver-checks repository right now. And I'll prove it to you by showing you exactly what is in this file. It starts with some metadata. It says, this is a major breaking change. We should deny this by default. Here's a reference link in the cargo reference that says why this is a breaking change. The biggest portion of this file is the details of the query, everything that we saw on the previous slide, plus one more block that just extracts the information for where, in which file and on what line that function was discovered. And at the very bottom, we have some error message templates. This is what shows us which function was the problem, what file it was found in, what line, and gives the user a little bit more context on why this is a problem. So this is what the user sees in the end. That's it. This is the complete file, the entire lint that cargo-semver-checks uses. Now, this is very interesting because somehow we didn't talk about most of the challenges that were in the previous section, right? We didn't talk about optimization and all of the crazy edge cases and stuff like that. We just wrote a query and we checked it into the repository, and now we're good. We have a brand new check for cargo-semver-checks to run against everyone's packages. That's the entire lint. The benefit for cargo-semver-checks here is huge. It means that with just a little bit of practice, anyone can write lints. You don't need to be an expert in static analysis or compilers or databases. It means that most lints can be community contributions. And this is really good for maintainability because this is something that's easy to read, easy to review, and very easy to compare against the rules of semantic versioning. So if some edge case got missed, it's not like it's buried in 10,000 lines of code. It's, a 50-line query lint that we can very easily read once and be fairly sure that we got everything correct. So anyone can write lints. That's awesome. It's also a very easy fix when the Rust doc format changes, because we didn't see anything of the Rust doc format in this query lint. The lints just don't change. When the Rust doc format changes, we make a small tweak to the adapter that we plug into the Trustfall query engine, and that's it. Because most format changes are fairly small, the tweaks are fairly small, and because we have hundreds of lints, we benefit because they don't change. We only edit a few lines in the adapter as opposed to a few lines times 100 lints. And once again, this is great for maintainability. So it's an easy fix when the Rust doc format changes. We also get optimizations that are applied automatically to all lints. When you write that query, you don't know if it's n squared or O of n, because the optimizations are not your responsibility. They're Trustfall's problem. And because it's not your responsibility as the lint writer to optimize, you can't forget to optimize. You can't get the optimization wrong. It means that the lints are very simple, and that also makes them very easy to review. And that in turn is good for maintainability. And again, if you want to see more about how optimizations work, I gave a full talk on that you can check out later, or ask me in the Q&A. And finally, the high performance that we get off of optimizations by itself produces downstream benefits. Not only do users appreciate this, but also it allows us to do the Semver study that I mentioned before, the one about how 1 in 6 of the top Rust crates has accidentally broken Semver. We were able to do that study without millions of dollars in funding because all it took was someone's laptop and like a week of CPU time. That's it. We would never have been able to scan 14,000 Rust releases if cargo-semver-checks weren't super fast to run. And along the way, we were actually able to proactively bug hunt for bugs in cargo-semver-checks itself. We were able to scan thousands of releases and also look for bugs and crashes in the tool. And because we were able to find those bugs before downstream users found them, it meant that we were in a good headspace to find and fix those bugs. We didn't have to do a lot of triage and worry about reproducing the user's problem. No, we had the repro and we had the skills to find it and immediately fix it. And again, this is good for maintainability. It's much cheaper to find our own bugs at a moment that is convenient for us as maintainers to find them. But not only is this good for us as maintainers, it's also great for users, because everybody loves a tool that is not only fast, not only does its job well, but also just never crashes for you. It's extremely reliable. So by this point, I hope I've convinced you that next generation dev tools are a database problem in disguise. This outlook on building dev tools allows us to take a domain where we have complexity everywhere we look, large domain, lots of optimizations, lots of edge cases, unstable data format, and dig out something that users will love using on a day-to-day basis. So Trustfall is a foundation for next-generation developer tools like cargo-semver-checks. Cargo-semver-checks is an awesome tool that is widely used in the ecosystem, and it helps you avoid accidental Semver breakage. And Trustfall is the tool that makes cargo-semver-checks possible. We would not have been able to build cargo-semver-checks if we couldn't treat the entire space as a database problem. Thank you so much for your time. And I put up some links that you might be interested in checking out later. We have some Trustfall playgrounds where you can write some Trustfall queries without leaving your browser. I've given previous talks on other Trustfall-based developer tools and how they work. And if this sounds cool and you'd like to follow my work or sponsor more development on Trustfall and cargo-semver-checks, I have links to social media. You can subscribe to my blog, or I have a GitHub sponsors page. And I'd like to thank everyone that has supported cargo-semver-checks and made it possible by sponsoring it. Thank you so much for your time, and I look forward to answering any questions.
Yeah, thank you for your talk. 1 second. Yeah. We have a bunch of questions, and 1 second, I have to check. Yeah, anyways, let's go through the questions. Another thing, I probably want to say is that our Yuri, I think, uploaded. Ah, okay. Anyway, somebody uploaded your presentation to resources section here, so anybody
Awesome.
who wants to refresh it right now can do that while we are talking about questions. And let me switch to the questions. So first question was, does it happen sometimes that new versions of the Rust compiler itself somehow cause your semver-checks to become outdated? For example, what if non-exhaustive rules changed somehow in next version?
Right. So the Semver rules by themselves don't tend to break, uh, except for cases where every so often we discover new horrifying ways of triggering breaking changes, but that's mostly on sort of me as maintainer of cargo-semver-checks and folks in the community to flag and say, hey, this is breaking in an unexpected way. Here's a reproduction. One example of that is that we somewhat recently discovered that uh, adding the copy trait implementation to an existing type is accidentally a major breaking change for entirely non-obvious reasons that I'm happy to share a link to if people want to find out. But it's not usually that the Rust language changes and makes something breaking all of a sudden where it previously wasn't usually. It's much more likely that a new version of Rust comes out. It comes out with a new format of Rust.json, and then I need to release a new version of cargo-semver-checks to support that format version. So cargo-semver-checks tries its best to be compatible with a wide range of Rust doc format versions. You can support, you can use today's version of cargo-semver-checks with many months old Rust versions, and everything up to current stable and current beta, and oftentimes, but not always, current nightly. But the breakage where the Rust language itself forces us to amend the rules is very, very rare. I don't think it's ever happened directly.
Okay, that makes sense. And I'll probably switch the order of the next questions because I want to ask first, aside from cargo-semver-checks, where else is Trustfall currently being used?
Yeah, so one example is that my previous employer uses Trustfall on the internal monorepo over hundreds of services and hundreds of packages to run lints like don't attempt to deploy a Python service that requests one version of Python in pyproject.toml on a Docker image that includes a different version of Python. So this is an interesting problem because the Python source code itself is fine. Its metadata by itself is fine. Its deployment configuration by itself is fine. The Docker image is valid and everything. But when you put the deployment configuration, the Docker image, and the Python service all together, all three of them together are not fine. And this is, again, a database querying problem because you can query the Docker file, you can query Python source code, you can query the deployment configuration, and realize that these three things won't work together, even though each of them individually looks okay. So that's one example. I'm building some other tools. I am building Semver linters for other query languages. I've built one for Python, which is not publicly available yet, but I do have a prototype, and I'm happy to share links with folks who might be interested in trying it out in the repos. And the TLDR of Trustfall is, everything that we've built so far will pale in comparison with everything we're going to build in the future. So it's more of this is an incredibly powerful tool that you should keep an eye on, rather than, this is something that is broadly accepted. I think that this database-centric view of dev tools itself is a fairly new idea, and that's why I'm excited to have given this talk.
Yeah, sounds great. And the next question is, what future developments or improvements are planned for the Trustful query engine?
Absolutely. A lot of the Trustfall query engine's developments are driven by the concrete demands that tools like cargo-semver-checks place on it. So these are things like being able to have more expressive queries, being able to do arbitrary transformations of the data. We already saw one transformation that's like count up how many things happen across this aggregate, right? we want to generalize that massively. We want to be able to support Rust's extremely expressive type system, and that will require being able to model arbitrary scalar types, because it's very difficult to model Rust's types as vertices with properties. We want to have more expressiveness there, and so we will be able to define a property called, type on a struct, field, let's say, and have that be able to be represented in the schema as a property rather than an entire, vertex and edges and everything like that. This is very challenging because that means that since we have custom scalar types, it means that we need custom operators over those types, right? We're going to want an operator like, is this type a super type of this other thing, right? I used to have type foo over here and I've replaced it with impl debug. Is that now forward compatible or not? So there's going to be a large breadth of functionality that will have to get added, and tools like cargo-semver-checks will benefit from every single thing.
Yeah, sounds great. Next question is, how does Trustfall handle complex queries while maintaining high performance? I also add like how actual indexes are created, if you have ones, like are they automatically designed or whatever?
Right. That's a great question. The full answer is, a half hour long. It's a conference talk in itself, and all of the details are in there, but I'll try to quickly summarize it here. So Trustfall by itself is like a database without a storage engine. It has no idea where the data is coming from. So it could be from an API, it could be from a local file on disk, it could be lazily evaluated, it could be a person with pen and paper feeding the Trustfall interface with all the data that gets requested. So the way you implement a data source for Trustfall is by implementing this adapter type, which is a trait that has 4 functions and 1 associated type, and it defines all of the operations that are necessary to execute a Trustfall query over a given schema. So these are things like, for a given vertex, evaluate its property value. For a given vertex, give me all of the neighbors across some edge, and so on. So these are some very basic fundamental operations like that. And it is the responsibility of the adapter to understand where its data is coming from and what, for example, indexes might make sense. Now, there's a fairly complicated dance that Trustfall and the adapter have to do, because Trustfall wants optimizations to happen, but it doesn't know whether indexes exist or whether the API you're querying has some more clever way to do a particular operation. And on the flip side, the adapter doesn't necessarily know what the user is trying to do. All it sees is the data source and the stream of requests coming in across this adapter trait API. So the way that it works is like this. The adapter is given access to Trustfall's internal query state. So the adapter, when Trustfall asks it for some data and it says, hey, give me the functions in the new crate, for example, the adapter might say, hey, by the way, the query that you're resolving right now, did it by any chance ask for the data along the importable path edge? And if so, did it have a specific path that it was looking for? And then Trustfall on the other side will say, why, yes, it was actually looking for this specific function, this crate : example. And the adapter says, okay, got it. And then it will use an index and it will only return that function. And then lo and behold, this is an O of 1 lookup as opposed to a lookup every function, look up every importable path for that function, and then discard almost all of them, which would have been sort of the naive implementation. So the TLDR of this is that the adapter builds the index, Trustfall offers information on how the query evaluates, and it is the adapter's responsibility to offer up its capabilities to speed up queries to Trustfall. Now, there are a set of optimizations that are not the adapter's responsibility, that are just kind of like always make sense to apply, things like lazy evaluation, for example, that Trustfall will do automatically, and those are always implemented regardless of what adapter you're using, regardless of the data source. But for things like indexes or predicate pushdown or batching or caching or things like that, those are the responsibility of the adapter. And so those are sensitive to the Rust.json format, and that's where we maintain them.
That sounds quite complex. Does it already have the stable API for that, or does it change?
Yes, it does. And that was actually the subject of probably the biggest recent change to the Trustfall query engine. Designing this API to make it so that it can express all of the optimizations we could possibly care to implement while also making it maximally simple is the subject of that other performance talk that I gave. You have to thread a very fine line because we want something that is very expressive but as uncomplex as possible so that we can keep it stable. We don't have to keep adding new functionality because we forgot to make some optimization available, while also making it as easy as possible to learn without losing any of the optimization expressiveness that we want. So yes, the API is stable. It's not necessarily the easiest to learn, but the subject of that other performance talk is that we made cargo-semver-checks more than 2,300 times faster by adding on the order of like 1,000 lines of code. And anytime you get to add 1,000 lines of code and get 3.5 orders of magnitude of speed up, I think that's worth it.
Yeah, sounds a lot of engineering fun.
Absolutely. I mean,
Yeah.
the optimization API under the hood, the Trustfall specific bits, not the adapter, they were something like 20,000 lines of code, implementation test cases and everything. So that took me most of last year, honestly, to design and build. So everything here that you've seen is very carefully designed with a lot of attention to detail because I hate breaking my own users and I especially hate buggy tools that don't do the right thing or behave poorly or have bad performance.
Yeah, looks like we have plenty of other questions. I have to just find the one where I stopped. So I think you have answered that at least partially, but I'll ask anyway. Does Trustfall use some database to store and execute queries on the graph, or does the model live only during the lint session? Looks like it's probably a question more for cargo
Right.
checks rather than Trustfall, as we already know.
Right. So Trustfall doesn't have an underlying database. It's not that you can't plug one in. It's just that it's designed so that you can bring the components that you need and it will not saddle you with anything that you didn't require. The data lives only in Rust.json. So when you run cargo-semver-checks, we get two Rust.json files generated, one for the old crate, one for the new crate. And then what Trustfall does via the Rust.json adapters is it binds to those JSON files, reads them into memory, and then runs queries across them. So there's no third database here that is involved. There's sort of the Trustfall query execution engine, the two JSON files, and nothing else. So we don't run some ETL into SQLite or Postgres or anything like that. That would be quite difficult and it would probably be quite bad for performance. So it's just all done on the fly over the Rust.json files. And in fact, the Rust.doc playground that I think I showed on the previous slide, it runs the exact same adapter and Trustfall code that cargo-semver-checks itself uses. So you can check out what that looks like. It's small enough that it fits in the browser. The browser just grabs a JSON file from GitHub, plugs it into some WebAssembly that, Rust compiled to WebAssembly that runs in your browser, and then all the queries run locally. That would not be possible if we had some other database like Postgres that ingested the data first before we queried it.
Okay, that makes sense. Can it happen that tests will show everything is okay, but in fact there will be errors that we will not see?
Yes. So cargo-semver-checks does not cover the entire spectrum of breaking changes. Like I mentioned, we have more than 80 lints and we keep adding more with every version, but we also have several hundred lints on the backlog that are not implemented yet. So if folks are interested in contributing lints, please jump in. We'd love that. I keep merging user contributed lints all the time. In fact, I'm going to merge one later today from a contributor. And there's a lot of work, like I mentioned, happening to make more lints expressible. So cargo-semver-checks, for example, will not catch type-related breakage yet, but there is a Rust project goal to make that possible in the future. So that's something that I'm going to be working on for the rest of the year and probably beyond. The idea, though, is that, you know, humans by themselves won't catch everything, and cargo-semver-checks by itself won't catch everything. But it's much better to have two tools that individually won't catch everything, because they will probably catch a lot of stuff that the other one didn't, right? So the 1 in 6 Rust packages having accidentally broken Semver, if they had ran cargo-semver-checks, we would have caught many more of those issues, right? Every single issue that we found in that instance was something that humans missed and the tools caught. Now, we don't know how many more issues there are that cargo-semver-checks would have missed and the humans would have caught, but certainly it's better to have both than to have either one by itself.
Yeah, makes sense. Next question is, can Trustfall be used for concurrent high-load real-time applications?
Absolutely. My previous employer used Trustfall in a variety of domains to query all sorts of things, from graph databases, large sharded SQL clusters, time series data, S3 APIs, everything you could imagine. I've written some blog posts on my previous employer's blogs on this. The keywords to look up are database agnostic querying is unavoidable at scale. I can put it in the chat up here. So you can check that out. And in that application, the Trustfall query engine did a lot more than what it does in cargo-semver-checks, which was unfortunately quite tied into my previous employer's systems. So it didn't survive the transition to, a written, like a Rust project written, separately from those domains. But the previous iteration would do all sorts of tricks, like when you write a Rust query, it would when you write a Trustfall query, it would directly compile it into SQL, and not only compile it into SQL, but also take it and slice it into subqueries so that it can run different pages all in parallel against a cluster to give you faster execution. And it would give you automatic pagination, so that if you requested some query and we didn't know whether you actually wanted all of the results, you'd get, say 1,000 results back, and then you'd get a continuation with a subquery that you could run, to get the rest of the data for what you started. This was super useful because our users would frequently write a query that would have too many results and might be too expensive. And so we didn't want to run it all at once and crash the SQL cluster, or make it unavailable for other users. And so this automatic pagination and automatic parallelization were hit features. Those are not things that Trustfall can do right now, but I am hopeful that in the future, Trustfall will be able to get a SQL backend or other backends that it can compile to, because Trustfall by itself doesn't care where the data is coming from. You can kind of see Trustfall as an LLVM for databases. So one way to execute Trustfall queries is via an interpreter and adapters and so on, like we see in cargo-semver-checks. But it's entirely valid to take the Trustfall internal representation and then turn it into, Cypher to run Neo4j queries, or SQL to run SQL queries, or anything else.
Yeah, sounds fun. And I think so far it's the last question. Rust Analyzer currently uses Salsa for storing project state. Could Trustfall be used to power Rust Analyzer queries? Would it be fast enough?
It's possible. I'm not super familiar with Rust Analyzer's internals. The direction I'm actually more excited by is sort of the opposite direction. If we could plug in Rust Analyzer into Trustfall, I think cargo-semver-checks and other related tools would get a lot of interesting capabilities as a result. One of the difficulties of type checking Rust, for Semver breakage across versions, is that it essentially implies re-implementing a lot of components of the Rust compiler by itself. So the importable path stuff, I had to re-import name analysis and import resolution the same way that Rust and Rust Analyzer both have it. And this is a giant piece of code in the cargo-semver-checks repository that has an incredible number of test cases and edge cases that we had to worry about. Now, if we have type-related lints, that also means, is this trait still implemented for this type given these bounds? And that sounds an awful lot like trait resolution. And that's something that Rust, the compiler, and Rust Analyzer both already know how to do to power everything that we see in our modern IDEs, all the little conveniences that we have. If we can leverage those and plug those into Trustfall and make them available into cargo-semver-checks, it would save us a lot of work, because re-implementing trait resolution is a heck of a lot more work compared to implementing import resolution. So I think, yes, lots of tools could be built on top of Trustfall, but I think the more exciting direction, rather than replacing existing tools with Trustfall-based implementations, is to take these tools that already exist and work really well and plug them into Trustfall to give other tools superpowers.
Yeah, that sounds interesting. And by the way, yeah, today we had another talk about writing these linters for Rust with Rust tools. And yeah, one of the issues with that approach is the one you have discussed here, like
Right.
the dependence on Rust version, and especially for the specific Rust nightly version in that case. Yeah, and
Absolutely.
it looks like Trustfall and cargo-semver-checks fixes that.
Right. And if
So
if we have more questions, I'm happy to go for it. Otherwise, I had a quick comment.
yeah, sure.
So if we look at the history of semver checking in Rust, it's actually quite interesting. There are multiple other projects that attempted to solve semver linting in Rust, and multiple of them have ended up being deprecated because the main issue was the maintainability problem and not the expressiveness problem. They could express lints just fine. These are tools like cargo breaking or Rust semverver. The main problem that they ran into was this sort of instability leading to high maintenance burden, where it was just very difficult to keep the lights on, as it were. You kind of have to sprint to stay in the same place, right? If you don't keep working on the tool and keep dragging it forward through versions, then everything just keeps breaking all the time. And I really think that offering better maintainability as the way to build more powerful tools is a rising tide that lifts all boats. I think that makes everyone better off as a result. Because I think the key challenge is not that we can't build really cool tools, it's that those really cool tools have to survive in the long run with very limited resources, with a very large footprint. Many people in the community use cargo-semver-checks. If 1% of those users had some sort of bug that we had to triage, or a difficulty in their use case, this tool would not be viable. I would have given up on it a long time ago. So I really think that's the key problem that we have to deal with. Maintainability is the thing that these open source tools live and die by, I think.
Yeah, that's true. Also, we have a comment from Andrei Listochkin. Is the Trust Analyzer and Trust Teams plan to migrate to a common trait solver in the near future? So it may take about 6 months to a year or something. Maybe, like I'd say, maybe even more. It doesn't matter. But yeah, I'm looking forward for like maybe Trustfall can somehow like augment that and use that.
I would love to be
I
able
don't
to
know.
use it. Yeah, it would save me a lot of work and a lot of learning.
Yeah. So I think we are done with questions. Thank you a lot. Thank you for such a long question session. And that was a great talk and great discussion and a whole lot of questions, I think.
It's my pleasure.
I think myself, I'll try to use Trustfall somewhere.
Nice. Feel free to open issues or ping me if anyone tries it and something is not obvious. Obviously, it's an open source project. It's very ambitious. That means that things are in a state of flux. The docs are always outdated, and so on and so on. So uh, contributions are welcome. I love helping people contribute productively and have a really good experience. So if you see something that's broken, let me know. I will try my best to fix it. And if you're interested in helping fix it, I will do my best to support you and make that an easy and pleasant experience for you. So if you're interested in checking out Trustfall, please do. If you're interested in writing some lints, jump into the repo, grab something from the long list of lints that we have. If the long list seems intimidating, please ping me on social media, and I will be very happy to find some lints that is not too difficult to implement that would be a good starting point.
Yeah, thank you. Have a nice evening or
Thank you.
whatever day you have probably.
Thank you so much
Yeah.
for having me, and thanks for all of the excellent questions. I hope you enjoy cargo-semver-checks, and thank you so much to everyone that put this conference together. It's awesome.